Hi guys. Um, we're going to talk today about complexation of drugs with compounds. And specifically, we're going to talk in more detail about when drugs complex with proteins. So that's going to be the emphasis of it, but we're going to talk about it more broadly first. This shows a picture of of a compound called cyclodextrin, where a drug this is a drug, it could complex with this little donut and could change the physical properties of the drug to try to make it easier to take or better to take or something like that, more soluble, etc. So that's one example of complexation that we'll talk about. So what is complexation? Well, it's just like what it sounds like. It's the interaction between at least two and maybe more, we're mostly going to be talking about two, compounds that could exist by themselves, but then they interact with each other. More generically, we would call the two compounds a ligand and a substrate. We're going to use the ligand to be a drug for most cases since we're pharmacists. So the ligand is a molecule that interacts with another molecule, the substrate. So in this case, it's usually going to be a drug and some kind of protein. So the drug will be the ligand and the protein will be the substrate. Drug molecules then can form these complexes with other small molecules or with macromolecules such as proteins, which is going to be our emphasis. Once the complexation occurs, the physical and chemical properties of the species are altered. So the compounds that were individual, when they're together, the qualities change. And we use this, right? So since it changes the properties of the drug, we can improve the solubility of an agent. We use this when we change a drug called theophylline into aminophylline to make it more soluble by complexing it with an ethyl-diamine. We can also improve the stability of compounds by using those donuts like I showed you the picture of earlier, cyclodextrins. We can improve absorption by complexing different agents. We can improve or inhibit the distribution of drugs. When drugs are bound to proteins, the proteins are very large so that when a drug is bound to a protein, it can no longer move around the body. We can also complex a drug or a ligand, a compound with another drug that would make it more hydrophilic or more lipophilic. If we want a drug to go out of the body, that's going to be usually in the urine. And urine is aqueous, as you know. So a drug has to be in a hydrophilic form, water-loving form, in order to be excreted in the urine. So we can complex a drug with a compound to make it more hydrophilic. And last but most important, the reason this is really, really important is when drugs interact with a receptor, that's when we actually have the effect of the drug, and that's a complexation. So at the end of the day, the drug's ability to actually have its effect on the body is a complexation. It's an interaction between the drug and the receptor. So we should really care because this is how drugs work. So we're going to go over a little introduction, which I've already started here. And then we're going to go into the types of complexes we see, which includes coordination complexes, which is covalent binding, versus molecular complexes, which is non-covalent binding. The coordination complexes, the covalent binding, is we're going to talk about metal ion complexes. So this is where there's a metal in the middle of the complex, basically. And then we'll talk about molecular complexes where we have non-covalent binding, which is the cyclodextrin complex that I've already mentioned to you, complexes, ion exchange resins, and then finally the most important one, which is the protein ligand or protein drug interaction. Then we're going to spend quite a lot of time on protein binding. So one thing that remains constant in all these situations is whenever two compounds are coming together to complex, there's always a capacity of the system, like how many of the receptors are around for whatever thing you have to bind to. So you have a capacity of the system, a number of sites where the drug or ligand can bind. So you're going to have a certain amount of substrate around. And then you're going to have a particular affinity, which is the attraction between the drug and the receptor, or the ligand and the substrate. So this is where we have our substrate. How attracted is it to these sites that we have available? So the more sites we have available and the more attracted it is, the more binding we're going to have. And this is what really determines how much binding you have, is the capacity of the system and the affinity of the system. All right, now we're going to just quickly talk about the coordination complexes, which are covalent bonding complexes, our metal ion coordinate complexes. So here's where we have a complex ion, a metal, and a ligand. In this case, it isn't a drug, but we have this metal, which is silver here, and ammonium here, two molecules of that, and so we have silver ammonia, I guess. I'm not sure exactly if that's how you say it. But this is an example of a metal plus an attached ligand. The ligand in this case is the NH3, but they will bind together in a covalent bond, using a covalent bond. The coordination number, so we have our complex ion, our ligand, and then we have a coordination number. Coordination number is the number of atoms or groups that can join with the central metal atom. So in this case, we have a silver ion, and it needs two ammonium ions to go to actually complex. So our coordination number in this case would be 2, wouldn't it? 2 right here. And here's a picture of it. Diamine silver. So our coordination number is 1, 2. And I should say our metal is silver and our ligand is ammonium. So I want you to be able to, for each of these, name the central metal ion, which should be pretty easy. If you look here, you can see it's iron, copper, cobalt, chromium, silver again, which is the same one we just did, right? And iron again. Where is our ligand? Our ligand here is cyanide, water, ammonium again, water, ammonium, cyanide. What's our coordination number? Well, here it's 6, 6, 6, 6, 2, 6. So that's pretty easy to do, right? You should be able to do this if I were to ask you on a quiz, but that should be pretty easy peasy. Now, the number of binding sites that each of these metal ions has available has a certain naming system. If there's just one pair of electrons that's available for bonding with the metal ion, it's called a unidentate. So it's only one pair of electrons that you can covalently bond with. So uni is 1, dentate is the number of electron pairs you have to bond with, and dentate, it means tooth. So I think of one tooth that it's sticking out so that you can bond with it. Bidentate is just that, 2 pairs of electrons, so 2 teeth. Bidentate. Multi or polydentate when we have multiple binding sites. These are called polymers. The most famous of these groups are called chelation agents. When you chelate metals, it's when you have complex forms when 2 or more of the same metal ion binds to the binding sites on a multidentate. And we use these for toxicity situations, that's when we see most of it. And EDTA is given for patients that have iron toxicity. So You can add this EDTA and it'll pull the iron in and make a chelating agent. So what we can see here is that we have iron with 4 hydrogens available, and then we have the iron EDTA with 6 waters and 4 hydrogens. All of these metal ion metals have ion coordinate complexes that we use as drugs. So I'm just going to go through a couple of these. Or in this case, this is hemoglobin, iron, and this is our hemoglobin, and it's a metal ion agent. So as you can see, it has a very, as you know, hemoglobin has a high affinity for carbon monoxide, which is higher than oxygen, and its real job is to carry oxygen. This is how people can die if they have carbon monoxide poisoning, because carbon monoxide has a higher affinity for those 4 sites to bind to hemoglobin than does oxygen. So you have to be very careful to make sure that you don't have much carbon monoxide around, because it will be preferred because of the high affinity. Remember, we talked about affinity and capacity of the system. Cisplatin and carboplatin are both drugs that are used for chemotherapy to treat different kinds of cancer, and they both have a platinum in the middle. They're metal ion complexes. It's actually a drug. This has cobalt in the middle, you can see here, and this is vitamin B12. All right, I'm going to stop.